Bismillah Rahman Rahim. So welcome to this lecture on FSMs. So remember that last time we discussed how to write the Verilog code for an FSM. Okay, and we discussed a very structured way of writing the code. So if you understand that structure, it will be very easy for you to write the code for any other FSM. But let's come to something more interesting and something which will really open up your vision and understanding about FSMs and how powerful they are. So consider this C code. This is your favorite algorithm for writing the factorial program. So you know what is a factorial. It is n factorial is n into n minus 1 into n minus 2 up to n. And the code is also very straightforward. So if you write in C, it will be int a is equal to 1, int b is equal to n. It is the number for which you want to find the factorial. So for example, here it is given that a is 1 and b is 5. So we want to find 5 factorial. So after first iteration, what we will have inside the loop, we have these two statements: a is equal to a into b. So in the first, after the execution of first statement, a will be 1 into 5 is 5, so a will be 5, and b will be b is equal to b minus 1, so b will be 4. Okay, so it is this statement. So this is our second statement. Now in the next line, we see there is a condition while b is not equal to 0. Currently b is 4, so we will go again into the loop. A is equal to, so now a is 5. Okay, 5 into 4 is 20, and b will become 3. So this is our third step, and so on. And finally b will be 1, but it is still not equal to 0, so we will go once again and we will multiply it. So you see that b is 1, so 120 into 1 is 120, and in the next one we will be done. So it is a sequential C++ code. This is how C++ code is executed. It executes in a sequential order. Now what if we want to write a code for this in FPGA? Let's say for some matter this is slow and you want to have a really fast factorial, and you have an FPGA board and you decide to implement it on the FPGA board. Then there are two main steps. One is that this design, okay, let's say we call it factorial design. This will have a data path, and it will have a control. So these are the two components, data path and control. And basically data path, by data path we means any arithmetic operation like add, subtract, or any kind of computation. This is data path, and control is basically our FSM. So we want to design a data path that can control our. So let's see how to design it. Let's first come to the FSM. So if I divide this code, I can divide it into several parts conceptually. So this code is for initialization. Okay, this is our main you can say this is our main computation part. and this is our, let's say, uh, done condition. Okay, let's say, let's call this initialization computation, and let's call it stopping or stop condition. So you see, I told you that in order to design FSM, the most important part is to recognize the states. And these are the states. Okay, these are the states. We have initialization state, or let's say start state. Then we have the computation, or let's say call it loop state. And then we have the stop condition, or let's say call it done state. This is what is shown in this figure, this state transition diagram. You see, this state transition diagram has three states: start, loop, and done. And then if you focus closely, then there is these statements. Basically, they show what happens in the data path, okay, or in your logic. So this is basically your registers. So all we need two registers. We need and from where I know this, that in order to store A, I need a register, and in order to store B, I need a register. Okay, so these are my physical registers which I need in order to compute this in hardware. Then I need for example this multiplier and subtractor and this logical operator. These are all the things that I need. So let's come again to the FSM. So we come to this, let's say, in the reset state. Okay, because hardware has clock and reset, so we need to denote the reset state. So if we press reset, we come to the start state, and you see this is a kind of you can say Moore FSM, because it is here. These are the things that needs to be done. So these are the output: A is equal to 1 and B is initialized to n. Okay, while then you see we come on the next clock cycle, we come to the loop state, and we stay in the loop until B is not equal to 0. So you see, this is exactly this condition. So until B is not equal to 0, we stay in the loop state and we continuously compute. And check this, these are the two lines that are here. So these are the two lines that come from computation. So this is the computation that is happening in this state, and we only move out of the state when B is equal to B is equal to 0. So we go to the done state, and then when we are in the done state, we loop here forever. So we loop here forever because we have completed our computation. So this is the FSM that we need, and the signals, and this is the data path. So I told you we need two registers. So this is my register A, and this is my register B. Okay, and then you see at the input of register is a mux. Similarly, at the input of a register is another mux. So let's call this mux. This mux is called W A mux. Let's call this, and let's call this mux W B, or let's call this one, let's call this mux A, and let's call this mux B. So these are the two muxes that control the input of the registers. And you see, because integer is 32-bit, so our register is also 32-bit, so it is 32-bit. Okay, so you see 32-bit input, 32-bit output, so this is our register. And then you see at the output of a register is our multiplier. Okay, and at the output of another register, B register, is our adder. So on this side we will be implementing this statement, B is equal to B minus 1, and on this side we will be implementing this statement, A is equal to A into B. So you see this line, okay, this line is B, this line is A, and this output is A into B. Okay, and if you check this line, this is A into B, you see this is going back to the mux. Okay, so this will be written back into register A whenever what? Whenever WA cell, which is our control line, when this is equal to 1, what will happen? This will happen, that in register A we will write A into B. Okay, what will happen when WA cell is 0? Then you see we are just writing A back, so we are writing A into A. Now why would we need this? Let's say that we have ended our algorithm. So imagine that B has become this, okay, B has become 0, and we want to stop the execution of the algorithm. So this is basically our stop condition. We want that whatever is in A, it should stay in A. So remember, in our example we were computing 5 factorial, so it is equal to 120. So when A is equal to 120 and B is equal to 0, we want that A is equal to A into B. This should not happen, because if it happens, then 120 into 0 will be 0. So this one, in this condition, we will say that WSL is 0, and this will happen in the done state. Okay, so we want to stop it, so this is one of the options. And you see, when WA cell is equal to 2, this is basically our initialization state, so we are putting 1 in A, so this is our init state. Okay, similarly, if you come on this side and we check the BMUX, so the BMUX, you see that WB cell, what happens when this is 0? When this is 0, B gets N. So this is again the initialization state, or the start state. When WB cell is 1, what is happening? When it is 1, we are just writing back B. We are just writing back. No, it is on 2. So what happens on 1? On 1, it is, this one is happening. This is on 1. So on 1, we are writing B is equal to B minus 1. So this is our loop state. And when WB cell is equal to 2, basically we are writing B is equal to B. So this is our stop state. So these are the signal values in different states, and here they are given in a fashion of our table. So you see we have 3 states. Okay, so if you want, you can write like this, that what are the values of different mux lines in these states. So I can write inside this, because if this is a Moore machine, I can write like this, that W a cell is equal to what is this in the initialization state? It is 2. Okay, and what should be the value of B cell at this point? The value of B cell in the initialization is 0. Okay, similarly I can write it this, that WA cell in the loop state, it is this one, it is 1. So this is my loop state, so this is 1, and WB cell is what? It is also 1. Then if I come to the third state, WA cell is equal to 0, and WB cell is equal to 2. Okay, so this is the complete Moore FSM. So remember that inside the Moore FSM we have outputs. And what are the outputs of my FSM? They are basically WA cell and WB cell, which are the select lines of these muxes, and each of this select line is 2-bit, because I am selecting among 3 different things at a time. So each select line is 2-bit. So my FSM is generating the signal. It has a clock input and it has a reset input. Now, one thing, I hope that you understand all the this part, which is our data path. And one thing is this comparator. Now this comparator is basically implementing the while statement. In fact, this part of the while statement, B is not equal to 0. So it is basically B is not equal to 0. This is basically checking this part. So you see, this is my B, okay, and I am comparing B with 0. So if it is equal, this is fed as an input to FSM, because this is the information on which FSM will know that the I have to go into stop state. You see, this is the only variable on which I am going from loop state to done state. So now I can very easily do it. The inputs to FSM is my Z signal. Okay, so this is my Z signal and the current state, and the current state is 2-bit because I have 1, 2, 3 states. So 0, this may be my 0, 0 state, this may be my 0, 1 state, and this may be my 1, 1 state. So let's see, if I am initially in the start state, which is 0, 0, and my Z is 0, which is says, what is my next state? My next state is 0, 1, okay, and my okay, you see on this line it doesn't matter if Z is 0 or 1. In both conditions my next state should be loop state. So I move from this state to this state irrespective of the fact that my input is 0 or my input is 1. Okay, on both 0 and 1 I move to the next state, and you see that what are the values of W cell. A cell, it is 2, you see 2, okay, and 2, and it is for B cell it is 0 and 0. So here I have written this. So this is my start state, this is my loop state. So if my present state is loop state, which is 0 1, then it depends on Z. If the Z is 0, then my next state is looping back. No, sorry. So this is what happens when Z is equal to 0, and this is what happens when Z is 1. Okay, because you are comparing because Z is like this one. Z is equal to A equal B equal 0. So, and the original condition is B not equal to 0. So that's the difference. If this is 1, then I must be in loop state, because here originally it is written not equal, and now I am using equal. So I could have used, instead of this box, I could have used this box. Okay, then the condition will be like the FSM. But here in the data path, they have used equality and not used inequality. So when Z is equal to 1, my next state is the same. Okay, and when Z is equal to 0, my next state is the done state, and I can set the values accordingly of the muxes. So you see it is 1, and WB cell is 1, so 1 1 1 1. Okay, so it's a moved FSM, that's why the values depend on the present state. And I hope that you understand what happens in the last state. So in the last state, you see we loop here forever. Forever means it is equal to 0 or 1, it doesn't matter. So on 0 and on 1, again it doesn't matter. If it is 0 or 1, we move to the same state. So we are inside an infinite loop because the algorithm has finished. And pay close attention to the signals. We have already computed our result, and we want that the result should not be disturbed. So when we want the result should not be disturbed, what we need to feed A. So A needs A. Okay, this is A needs A. So this happens on 0. So you see it is 0, and you see here it is WSL is 0, WSL is 0. And what should happen to B? B should, you see it is 2, which is this one. So you see B gets B. So that's why 2. So this is the whole control. You see, this is like a small computer that you have developed. On the left hand side, you have a very beautiful architecture for computing our factorial, and on the right hand side we have the whole control unit. So this table is in fact the control unit. And from this very small example, you should imagine how your computers are designed. And we already studied in VLSI course that we can implement an FSM very easily with a ROM. Okay, and if you remember in VLSI course, there was an FSM for an int miss. Okay, and we discussed the design of the FSM, and we discussed how to map it into a ROM. So the same goes here. We have our input to FSM, which is Z. We have the output of FSM, which is WSL and WBSL. Both of these lines are 2-bit. My Z is 1-bit, and then one output is of the FSM is my next state, and one input of my FSM is current state. Again, this is this table. So this is the table from the previous slides. So we need a ROM that has 8 locations. So it should have 8 locations, and each location should be 1, 2, 3, 4, 5, 6 bit. So we need an 8x6 ROM. Okay, and we need so this is 2 bit, this is 2 bit, so this is basically 2 D flip-flops. Okay, this is 2 bit D register. This is all I need. I need to initialize the contents of the ROM with this. So at 00 address I need to write this, at 01 address I need to write this, and this is all I need. And by now you should be very familiar, because in the first 2 weeks we discussed in great detail how to implement any function with a lookup table. So we also discussed that a lookup table can be used to implement a ROM or a RAM. So this is exactly what it is. So we can use this ROM and we can implement it in our FPGA using our lookup table. Okay, and again, this is an interesting question, that if I need to implement this ROM with 3 LUTs, okay, let's say with 3x1 or with 3x2, how many LUTs will be required to implement this ROM? Okay, so you can go through that and try to implement it with LUTs. Okay, so this is one part of my lecture, which was about design of FSM. In the next part I will move to a more complex example. Let's say we want a machine that can not only compute factorial but also compute other functions. How we can do it? So in a more broad sense, the next lecture will be about how digital computers work, or what is the basis of digital computers. Okay, so see